Find two numbers a and b where a is less or equal than b, whose difference is 30 and whose product is minimized. Let's start. We need to create a model where we will have two equations. One will be an objective function. That is the function that we need to optimize, in this case, to minimize. And constraints. Constraints are basically restrictions. Well, since the function we want to minimize is the product of a and b, then let's write it down. A times b is the product we need to minimize. You can call it f if you want. You can call it p as product. I'll call it f. Well, I know that this should be to minimize. It should be minimized. Minimize. Now, the restrictions are that the difference should be 30. Thus, I will write this down. A minus b is 30 or b minus a is 30. Well, that's why they gave us this little note, that b should be greater than a or equal, and that should be equal to 30. That means a and b are not the same anymore, since 30 is not 0. And this is the model. Well, let's name first of all equation number 1 and equation number 2. I like doing that. Let's use equation number 2, which are basically constraints or restrictions, to solve for one of the variables. I guess I will choose to solve for b. Solve for one of the variables. Okay, in this case, b looks easier. B will be 30 plus a. Now we're gonna substitute. Let me probably make steps for you. Step 1, create a model. Step 2, solve for one of the variables using constraints. Step 3, substitute into 1, which is objective function. F that used to depend on two variables a and b now will be a stays as a, but b will be changed to 30 plus a. We did this because we plan to differentiate this function to minimize it, right? Find the critical points and proceed with first or second derivative test. So it will be easier to do it if it has only one variable. Let's simplify. 30a plus a squared. And this is the function that now only depends on a. 30a plus a squared. And the calculus starts now. Step number 4 is to optimize. Optimize via derivatives. Derivatives. Let's find the first derivative, and it's going to be 30 plus 2a. Now you can choose what to do. You can do first derivative test or second derivative test. If you perform first derivative test, you can sketch the sign line. You can solve for critical points first. Let's actually do that anyways. Critical points are coming from zeros or D and E points, but it's a line, so there's no D and E points here. We want to find for which a we will have 0 when it is 30 plus 2a. 2a is negative 30, a is negative 15. This is a critical point if it's in the domain. Well, it is in a domain here. So now, well, it was never stated that a and b should be positive, for example, and there's no restrictions except the difference should be 30. Now, choose the method. I will choose probably for second derivative test. Second derivative test. It's kind of easier to work with second derivative test when numbers are easy, and also when the function is easier to differentiate second time. Second derivative test, as you can see from the name, this requires second derivative. It will be 0 plus 2, which is 2. And the idea is you need to plug into second derivative the critical point you found, and check the sign. If the sign is positive, then the original function, I usually tell people, I I usually tell people like so. The original function is happy because of the second derivative being positive. Thus, it's concave up. And the point here is the minimum. It's a tongue of the smiley face. If the second derivative is negative, then you can have a grumpy face. Then the original function is concave down. Again, it's f. It's not the f prime prime. And you have maximum at the nose. And that's how you work with it. Well, maybe you have noticed that no matter what I plug into the second derivative, it still gives me 2. So I can say that f prime prime at negative 15 is still 2 because it's a constant. That doesn't really matter that it is 2. What matters is that it is positive. Thus, original function f of x, which is, what was it? 30a plus a squared. 30a plus a squared is concave up. Thus, a equals negative 15 is local minimum. See, it's at the tongue over here. Well, the thing is, it's a local minimum and we want to find the global minimum. How do we know that it is the most global minimum out of all the minimums? Well, there's no other critical points. Note, since there is no other critical points, this local minimum is global minimum. Like so. And also you can check that the function, the original function a squared plus 30a behaves like so. It's a parabola. F equals 30, I will even rearrange it for you. A squared plus 30a. That's a concave up parabola. So it is always going up from both sides. Or you can say that it is decreasing, reaches its local and global minimum, and then increases. Thus, you can claim that this is a global minimum. Global minimum is happening at a equals minus 15. For you to know, also very interesting, that x-axis here is actually a-axis. And y-axis is f of a, for you to know. Anyways, we need to find another value. That will be step number, so we have step number 4. We found the critical point. Step number 5, choose the test to classify this critical point. And step number 6 is justify that it is indeed global, not a local minimum or maximum. Finally, the last step is to finish the problem. After this, you just need to find whatever they ask you to find. They ask us to find both a and b. So, find b. B had the formula, remember? It was minus a plus, no, it was a plus 30. A plus 30. Let me check that. B, yes, see, I put it in the box. 30 plus a. And that gives me minus 15 plus 30, which is 15. Answer. A is minus 15, B is 15, and we can even check. So B minus A better be 30 because that was the condition. Well, 15 minus minus 15 is indeed 30. And then the largest product will be 15 times negative 15. Interesting. For these two numbers, we will have product, so F was A times B, which is negative 15 times 15, which is negative 225. How interesting. How odd. Oh, it was not the largest. It was the smallest. I now remember. They told us to minimize. To minimized product. of these two numbers. And this is how you work with optimization problems. You create a model, use the restrictions to solve for one of the variables, substitute in the objective function, start optimizing it using calculus knowledge, justify it, find all the other variables that were asked that you need to find, and claim the answer. Good job for working hard.